Good afternoon, my name is Captain Herrera, and this is Captain Barker. We're going to give our presentation on lab number 2, where we determine the acceleration of gravity by dropping a steel ball. So here's our outline. I'll give you a second to read our outline. So at the very bottom, you can see we have our executive summary. This is our bottom line up front to what we determined during our experiment. So we determined that our acceleration of gravity will be 10 plus or minus 2 meters per second squared. While this may be accurate, it's not very precise. So during this presentation, we're going to talk about what findings we may have discussed and why we have some sources of error within our experiment. So here's our materials and methods. So we are using the base physics of kinematics. So we'll talk about how we can really apply that during our experiments. But we're going, during this lab, the experimental will change the height of a steel ball and drop and measure the corresponding time of the fall. The experiment will then compare the time of flight for a launched steel ball to that of the initial time of fall. Using the process of linearization of a model equation, a formula will be used to calculate the acceleration due to gravity. So here's our general setup. We're going to be dropping a ball at a given height and then measuring that time of the fall. And in the second phase, we're going to launch that ball with a given horizontal velocity and then measure the time of flight for that ball to drop that same y component at the same vertical height. So here's our 3 phases for our presentation. The first phase, we're going to look at 1D kinematics. We're going to look at just dropping the ball in one dimension. The second phase, we're going to look at 2D kinematics. We're going to be applying some type of horizontal velocity using a projectile launcher and measuring that time of fall at same vertical height, same vertical distance. The third phase is we're going to compare both results and see what the difference may be and maybe some sources of error within that experiment. So our objective quantity is we're trying to solve for the acceleration due to gravity. So that's the purpose of this lab, is what we're trying to accomplish. Our base equations, we're going to use our kinematic base equation, and we're going to make a couple assumptions to make that simplified. So we made the assumption that the vertical height will be 0, and that the acceleration, that the velocity in the vertical component will also be 0. So we made the assumption that we're going to drop the ball from 0, and it's going to pick up speed as it goes along using the acceleration of gravity. So using those assumptions, we can make some simplifications. So we are varying our height and measuring our time. Once we go through the linearization, we come up with our linearized model equation. So t squared is our dependent quantity, and our independent quantity is going to be our height, our vertical distance. At the end of the day, our slope, our step 8 of our linearization will be our acceleration of gravity, which is 2 divided by the slope. So that's what we're going to use to solve for our acceleration of gravity. So in our results and discussion, so we are comparing 1D versus 2D kinematics. We understand through kinematic or kinematic equations that our x component and our y component are independent of each other. So even though we fired our ball horizontally, it does have a x component. The ball should still fall given the same rate in the y direction. So it should have the same time of fall for both 1D and 2D kinematics. In our actual experiment, we see that there is actually a slight discrepancy between our time of our vertical drop and our time of our horizontal launch. While we think these should be the same, they're different. They do overlap a little bit, but they are slightly different. So one reason you might think that they actually have a discrepancy in there, because even though we made the assumption that our ball is going to drop from 0, the time we actually released the ball and actually passed through the photo gate, that ball did actually pick up a slight vertical component of our velocity. So while we made the assumption of 0, during the experiment that wasn't exactly the case. So that may lead to a source of error for our overall acceleration of gravity.
Carrying this over to our results and discussion, we have a total of 6 measurements, varying heights. As per the procedure, it was between 1.2 to 0.2 meters. You can see the measurements that we have at this point for our initial height of drop. Carrying that over to our independent quantity versus dependent quantity, we're looking at the height of the drop versus the time of the fall squared. This data provides the following trend line with a slope of 0.19 plus or minus 0.03 meters, seconds squared per meter. 2 points that I would like to bring to your attention. The first one is this upper point right here. The second one is this bottom point right here. These 2 points differ greatly from the remainder of the slope, which leads towards our error analysis of the slope itself. As you saw from the objective formula, slope is the only variable in its calculation, thereby having the predominant and only source of error in the final calculation. When we're looking at our at our slope itself, as you can see, it has a 16% relative uncertainty, which is rather large. However, when using it, when inputting that value into the objective formula, we get a acceleration in the vertical direction of 10.186 meters per second squared for our acceleration due to gravity. Because of the nature of the equation, we use the uncertainty in products and quotients, which allows us algebraically to derive the following equation. Inputting the values that we have for or substituting in the values we have for the slope, the uncertainty due to slope, and the acceleration due to gravity that we calculated, we obtain an absolute uncertainty for the acceleration due to gravity to be 1.64 meters per second squared. Carrying that over, we get the confidence interval for the for the experimental value of the acceleration due to gravity to be 10 plus or minus 2 meters per second squared. When doing a number-line analysis, it's very clear that we have an accurate value based on the overlap between our experimental value and our accepted value. We also see that the predominant source of error in our experiment is random error. One of the biggest questions at this point is how to make our experiment more precise. As we mentioned earlier, slope is the largest contributing factor and the only variable in our final objective formula, therefore making it the primary variable that we need to look at for relative uncertainty analysis. In order to improve this, the height of the drop and the time of the fall are the two factors we need to look at. With respect to making it more precise, every time we did the measurement, we said, okay, this is the height we're dropping it from. We measured it as close as we could to the photo gate. However, we kept dropping it a little bit above the photo gate. As Captain Herrera mentioned earlier, with our horizontal versus our vertical component for our drop versus launch of a ball for exploring 2D kinematics, we need to find a more precise way of making sure that we drop the ball with an initial velocity of 0 at the photo gate to measure the most precise time. Additionally, this would increase the accuracy of our height measurements, resulting in a little bit less uncertainty in the overall experiment. We'd like to give a real quick nod to Cadet Awesome. He pointed out that we were dropping the ball right above the photo gate instead of at the photo gate. When we did some of our experiments, this helped us identify ways to improve the experiment. However, we ultimately still had some more work to do to make it a much more precise experiment as a whole. Any of your questions, sir or ma'am? This concludes our brief. Hey there, physics fans. By now you've watched the example presentation done by myself and Captain Herrera. While this is an example of a good presentation, it is not perfect on purpose. Several errors were inserted to serve as teaching points. The errors we identify in this AAR are not all-inclusive, merely highlights we want to bring to your attention of common presentation errors. There are multiple ways to attack a good presentation. Although this presentation was a good presentation, there are many things we could have done to make it a little bit better. Items that we could have done differently include a history or background of the subject matter, an arrangement of some of the slides, and topics covered by which of us, and how we did them. No matter how you design your presentation, the important thing you need to remember is to practice, practice, practice.
Hi, so on this slide I went over the outline as well as the executive summary. So this is where I was trying to convey to the audience the flow of the presentation. And normally this is also known as the bottom line up front. We want to be able to give the audience an idea of what is to come, so they have an idea, so they know the flow of the presentation so they can easily follow along. There's many different ways to approach this slide, and this is just one of them. On this slide, you saw me reading directly from the slide. I was walking in front of the board, I was also talking to the board. When you're giving your presentation, you're giving your presentation to the audience. So the slides are simply there as talking points. Use them as reference. They're your visual aid. So when you're giving your presentation, don't be talking to the slide, but talk to the audience. They actually want to know what you have to say. On this slide, I used some animations. I was able to use an animation to help show how I simplified my base equation. So make sure your animations actually have a purpose. Too many animations can be very distracting to the audience. So while you are designing your slides and make sure how you want to present, you can use your animations to draw attention to what you're trying to bring a point to. But at the same time, make sure it's not distracting. If it's too distracting, your audience will lose focus and start focusing on what is on the slide and not listening to what you have to say.
At this point, we switch presenters in order to highlight how we could do a transition. There's multiple ways to do it. The important thing is for you to practice. If you're going to do a presentation and include a data table, make sure it's legible and make sure it tells a story. If you remember, at one point in this portion of the presentation, we had highlighting going on for the data table, as well as 2 different data points identified with arrows. Those points tell us very clearly to the audience the exact points of error that you want to convey and why those points are important. The animation helps with this flow, so you remember to highlight and discuss those aspects. Additionally, you'll also notice that we switched from using a pointer with Captain Herrera to using a laser pointer, but you couldn't identify the laser pointer as I was using it. If you're going to use a laser pointer or any sort of pointing method, make sure it's visible and clear to your audience. If it's not visibly distinctive, your audience may not be able to see it. If you're going to build a table, make sure it's accurate and neat. The table format we used here was one that you're very familiar with because we've used it for almost every single lab this semester. We can very clearly orient you to where the relative uncertainty is. We can very quickly orient you to the objective value as well as how to calculate the absolute uncertainty. It clearly communicates exactly what you want you to take away, which is the importance behind how to build a data table to an audience that's listening to your information. If they can't take away what you want them to understand, you need to find a better way to design it. A picture is worth 1,000 words. This picture illustrates more than any other point throughout our entire presentation the accuracy and precision that we talked about with the bottom line up front. Captain Herrera very clearly identified the different aspects of the presentation as far as what we wanted you to take away at the beginning, but this is where the entire idea of the precision versus the accuracy of our measurement comes to light. Finally, we did our works cited slide. This lends credit to others and increases your academic rigor as well as the credibility of your work. It's not a bad thing to do, and it should be done by every cadet if they receive assistance. Additionally, I want to talk about hidden slides. While you're doing your presentation, you're limited to 10 slides in 10 minutes. These 10 slides in 10 minutes are all you should be handing to the instructor if you hand them a slide packet. However, during the 5 minutes of questions afterwards, the instructor may have specific questions, and you can have hidden slides to help reinforce those points. Please consider those when you're preparing a slide packet, as you may print off your slide deck and accidentally include a hidden slide that should not be included unless you need it. This concludes the AAR of our brief. As a final reminder, our AAR is not all-inclusive, but highlights key briefing errors we want you to avoid. Good luck as you prepare your presentations, and remember to practice, practice, practice.